If you take a look around you, one thing you will definitely notice is that virtually everything you see is man-made. Everything from buildings to clothes to computers.
To cars, roads, and everything in between. Humans have definitely learned how to make our lives more comfortable, reliable, and safe through innovation. Hi, I'm Jennifer Pulley.
And I'm Johnny Alonzo, and today on NASA 360, we're going to take a look at how human ingenuity is making man-made objects stronger, safer, and much more available for all of us.
For thousands of years, humans have taken objects from nature to create a better world for themselves. Take, for instance, mud bricks from antiquity that were used to build dwellings.
Through trial and error, early carpenters learned that just building structures from plain mud often led to unstable structure. But when they combined mud and straw together, they came up with a new structure that resists both squeezing and tearing, resulting in a much better dwelling. Although they may not have known it, these early builders were using composite materials.
Even though the use of the term composite materials is generally synonymous with space-age materials, composites, they've been around for a long time. Basically, a composite material is formed when you combine two or more items that have very different properties. Many composites are made up of just two materials. One that acts like a glue to surround and bind, and one to reinforce like fibers or fragments. When combined together, these different materials usually work together to make the sum of the parts much better than the original materials alone.
Today, the use of new composite materials can be seen in virtually all space-age designs, from new aircraft used by you and me, the general public, to even next-generation spacecraft for future space missions. Now, this turn to composites is because weight reduction combined with strength has always been a critical goal of flight, even since the beginning.
The first aircraft ever made were built from wood and fabric material, but it was soon realized that a major change needed to be made to increase the strength and durability of aircraft. The change came with the introduction of strong and lightweight metals like aluminum. Since that time, the use of these types of metals have been the state-of-the-art for both aircraft and spacecraft.
Today, metal spacecraft are still state-of-the-art, but researchers have begun to look at new ways to build spacecraft that could offer better alternatives to metal. In fact, NASA is already testing what could be the next big step in spacecraft design. Right here at NASA Langley, it's called the Composite Crew Module, or CCM.
I met up with NESC Principal Engineer Mike Kirsch to find out a little more about this innovative design.
Mike, this CCM to me looks a little familiar. I mean, I'm thinking 60s Apollo capsule.
It's very similar to the Apollo program. Many shapes will work for the mission that this was intended, but in order to kind of streamline the decision process, the Apollo shape was picked. And that way we could leverage the aerodynamic data that we collected during the Apollo program. So this is a slightly larger version of the Apollo. The Apollo is roughly 4.3 meters in diameter, and this one's 5 meters in diameter. If you recall, Apollo had 3 astronauts on the inside. This was designed to carry 6. Later lowered to carry 4, but the volume is still there to carry 6 crew to and from station.
Mike, we've been talking a little bit about composite materials. What type of material is the CCM made of?
This is a carbon graphite epoxy resin system. It's a fabric that was hand laid up on a male tool. And then you put the entire system into an oven. It's actually a pressurized oven called an autoclave, and it gets cooked and it comes out hard.
Let me just kind of make sure I understand this. Kind of like a wire mannequin wrapping fabric around it. Is that kind of what?
Yeah.
Okay.
Yeah. That's a very good analogy.
Okay.
And then that's only the first step, though. So after that, we add what's called an aluminum honeycomb. You glue the honeycomb to the skin, and you cure that. And then after that, you lay another skin on top of the aluminum honeycomb. And then you put that back in the oven and you cure it. And when it's all done, it comes back as an assembly. So you have a thin skin on the inside and an aluminum honeycomb in the center, and then another thin skin on the outside. And it's rigid and cured just like that.
And you know, as you're describing this to me, I'm thinking, wow, that's a lot of stuff. But this is, I mean, I can barely feel this.
It's very lightweight, which is the idea of composites. It's a high strength and stiffness to weight, which is one of the objectives of the project. The purpose of the project was to get some NASA guys some hands-on experience designing, building, and testing with composites. Now, this is an alternative to the mainline program. The mainline program, which is Constellation, in particular the Orion project, which makes the crew capsule, they chose aluminum lithium, which has very similar strength and stiffness to weight characteristics. But this is an alternative, and by using composites, it enables complex shapes to be made. And to give us a real-world comparison between the aluminum lithium mainline program against composite structure of using the same set of requirements.
Mike, you said earlier that composites allow you to test different complex shapes. Talk to me about the CCM shape. Why this shape?
When the project was kicked off, we tried to respect the interfaces that the Orion project was using for their crew module. Now, Orion at that time had baselined this component called the backbone. And this backbone was really used to help them manage the stuff that goes inside the capsule. What the composite team did is we tied our floor to this backbone shape. Then the next thing we did is we actually shaped the floor to take advantage of the fact that the backbone was there. And what it did is it brought in these lobes, and the shape of the lobe is the shape that the floor would want to take when pressurized. If we didn't have the backbone, we didn't have the lobe floor, then what happens is it would be a dome-like shape. When you pressurize a dome, it wants to go to a ball shape, a sphere. And by tying it to the backbone and putting in the lobe shape, we could reduce the stiffness in the edges, which saved mass. Now, the composites don't inhibit aluminum lithium from having a similar shape. It's just much more difficult to put a lobed shape into an aluminum lithium system.
Mike, what are some of the reasons people use composite materials?
Well, composites are known for their strength and their stiffness for mass. So they're very lightweight materials, and they're used oftentimes in the high-performance industries. Composites are also thermally stable. What that means is that they don't change shape as they change in temperature. Composites are also very tolerant to fatigue. Any application where shape is of critical importance. In the airplane industry, they like it on a wing. They want to manage the shape of the wing, the mast of a sailboat, the hull of a sailboat, the racing sailboat, tennis rackets, racquetball rackets. All of those use carbon fiber because they're very, very stiff, very, very lightweight.
Mike, any tests to failure to see if the CCM would completely fail?
Absolutely, and part of the program was to pressurize it until it failed. And we pumped it full of water with that same set of instrumentation on there and continued to pump it up until it actually cracked or popped. Now, we were expecting a fairly dramatic failure. All of our predictions were that it was going to be dramatic, and it turned out it was not very dramatic at all.
And is that positive?
That's a very positive result. Now, this was designed to dock to the International Space Station, so it's designed for an internal pressure of 15 psi, just like we're breathing here on the ground.
Right.
But you actually multiply that by 2, so you have a little bit of margin, some what we call a factor of safety. So it's actually capable of 31 psi to be where we were comfortable. It actually failed at 53 psi, significantly higher than its design ultimate capability. But that shows that we have a fair amount of damage tolerance still remaining in the design. This project's been extremely successful since its inception, and we're very excited about where it goes from here.
Mike, thank you so much. How exciting. We're standing by to see what happens.
All right.